Hello, all the crazy people out there. My name is Michael. I like wizards and dragons and making games, and when I was looking through the archives of the various GameMaker video subjects that I've covered in the past, there is one that I actually kind of couldn't believe that I haven't talked about yet, and that is going to be Bitwise Arithmetic slash the various Bitwise operators. So, where the arithmetic operators, things like plus, minus, multiply, divide, that sort of thing, while the arithmetic operators allow you to do different mathematical operations on numbers as a whole, the bitwise operators allow you to do a different set of operations on individual bits inside a number. So, I'm guessing that most of you are probably at least somewhat familiar with this, but just in case anyone's not, probably the first thing that a lot of you learned about how computers work is that instead of storing numbers internally in the computer's memory as like actual decimal values, for example, written out, that's not the numbers, written out using the digits 0 through 9, computers, by their electronic nature, will instead store numbers in a base 2 binary format. So they can only use the quote-unquote digits or the bits 0 and 1, representing different like electrical voltages inside your computer RAM. And by and large, this works exactly the same way that counting in base 10 does. For example, you can count from 0 to 9. I am actually going to increase this font size further, I think. But if you want to count to a number that is bigger than 9, bigger than what you can represent with a single digit, you would have to carry over a place value, and you would have to start over counting in the tens place, and then from there you could continue until you carry over again. I do not like how big this gutter is in this text editor at 400%. This feels like very weird and claustrophobic. So that's base 10. I'm sure that brings back some good memories of learning about place values in like first grade. So base 2 works exactly the same way, except instead of being allowed the digits 0 through 9 when you're counting up in any given place value, once you get to 1, if you want to represent a number bigger than 1, you would have to carry over and begin a new place value from here. So this bit pattern 10 represents the number 2 in base 10. If you want it to keep going, the bit pattern 11 represents 3. If you want to add 1 to that, you have to create a new place value. And I think I will add a couple of leading zeros here just to really sell the effect of what we're doing here. This bit pattern 100 is 4, 101 is 5. If you want 6, you have to carry a place value over. 7, 111, 8, 1000. So that is counting in base 2. And if you wanted to take this bit pattern and turn it back into like a base 10 number that you probably are a little bit better at understanding, you can do the classic place value thing where you assign each of the, in this case, bits in this number an ascending power of 2, and then you multiply the values at each place value by their respective power of 2, and then add them all together. When I was in like first grade, we did that in math class. I thought it was the most pointless thing ever, but now that I actually do sometimes work with numbers in different base systems, that actually makes sense. Anyway, the first bit is going to represent 2 to the power of 0, in the same way that in a base 10 number, the first digit would represent 10 to the power of 0. The second bit is going to represent 2 to the power 1, again, in the same way that in a base 10 number, the second digit would represent 10 to the power of 1. The third bit is going to be 2 to the power 2 is 4. The fourth bit is going to represent 2 to the power of 3, which is 8. The fifth bit is going to represent 2 to the power of 4, which is 16, 32, 64, 128, 256, and so on down the line. And if you have a number in base 2 that you want to turn into a base 10 number, you simply multiply the bits at each place by that place value, and then you add them all up. So in this example here, it's a little boring. All we have is a 1 in the 2 to the power 3 place. So this number here is going to represent 8. If you had a more, let's say, a more elaborate number, this is going to be 1 times 2 to the power 0 plus, that's going to be 2 raised to the power of 1, which is 2, so 2 plus 1. There is no third bit, so you don't worry about 2 to the power of 2. The fourth bit is a 1, so we're going to add 2 to the power 3 on top of that, which is 8. So 8 plus 2 plus 1, this number represents 11 in base 10. Of course, if you want to do actual arithmetic on these numbers, it works largely the same way that you would do arithmetic on numbers in base 10 or any other counting base. So if I have this number here, and if I want to add, let's say, this number here, which I believe is going to be 6, If I want to add these up, we can do the same thing that we do when we want to add numbers in base 10, except instead of doing a carry operation once you get to like 10 and roll over, we are going to do a carry operation when we get to 2, because we do not have a number representing the number 2 in base 2. Anyway, so 1 plus 0 is 0. I mean 1. Off to a great start here. That's going to be our lowest place value. 1 plus 1 is 2, and since we do not have a number 2, we are going to insert a 1 there and do a little carry operation. 1 plus 0 plus 1, that is also going to be 2, so we're going to have to do the same thing. The new text editor does not seem to want to allow me to, like, backspace one space at a time. Anyway, we're going to do another carry operation there. We have another 1 and 1 and 0. That is also going to be a 0, and we're going to have to carry another 1. 1, 0, 0 is going to be 1, so this is going to be, I want to say 17. And if you want to check my homework, you can verify for yourself if this bit pattern does represent 17. Anyway, I'm not going to go over things like subtraction, multiplication, division in base 2 because I think that's getting a little bit besides the point. What I really wanted to talk about is other things that you can do with numbers in base 2 in computers. So, let's change gears a little bit, and let's imagine that you have in your game a player character. And let's imagine that your player character has a couple different attributes to go with them. For example, you might have properties such as can, run, which might be a true or false. And maybe you have another one that is can swim, which might be a true or false. And let's say you have a fourth property, for example, can fly. That's also going to be a Boolean true or false. And lastly, just to keep things interesting, can eat dairy. And we're going to imagine that all 4 of these properties are actually important in your game. We'll pretend that, I don't know, the healing potions are based on like mozzarella or something. This is the world where the Italians ended up achieving world domination. Anyway, these are a set of 4 true-false values, and in this case, as I've written them here, and as it would probably be fairly natural to write them out in a game in everyday life in 2026, you're going to use 4 separate variables for each of these true-false values. But something else that you can do is, instead of having 4 variables which individually represent a true or false value, you can string these together into a single value, and we can, let's say, write out the bit pattern, in this case, 1, 0, 1, 1. And again, because we are imagining that this is some property of the player character, let's make this look like code, actually. Maybe we can just call it, like, abilities. And now, instead of having 4 values, which represent the things that the player can do, now we just have 1 value representing what the player can do. So the real fun here begins when you see a number like this. Instead of thinking of it as an ordinal or a cardinal number as you ordinarily would, like a number that represents a value, like the number 5 or the number 11 or whatever this is, but you instead start thinking of this number as an array of individual true, false, an array of individual bits, then you start to wonder, what can I do to individually manipulate or individually access a single bit inside this number? If I wanted to take this number, if I wanted to take this mask as it's known, this bit mask, and if I wanted to extract the information of whether or not the player is able to fly from this value here. And to do this, we are going to take another little field trip into the realm of regular true-false values. So this is another one of the probably first things that you learned when you started getting into computer programming. If you have 2 values, value 1 equals true, value 2 equals false, you can do things such as, like, if value 1 and value 2, we're getting italics here in the text editor. I opened up this, like, I'm using a note asset instead of a script asset because I didn't want, like, formatting or, like, weird colors or red squiggles when I started typing code that isn't code, and now it's just, like, italicizing these values anyway. Anyway, in pretty much all computer languages, you have operators for logical and. You could also use double ampersand in GML instead of the and keyword. You also have the or keyword, or alternatively the double pipe symbol for or. You've got equals equals, always a fun one if you want to check if one value is equal to the other. Not equals, you've also got, and this is much more rarely seen, but XOR, which really boils down to just not equals in Boolean logic.
Hey.
If one value is not equal to the other. You don't see that one very often. Anyway, you can do pretty much the exact same operations on, instead of numbers that contain a single true or false value, these Boolean values like this, you can do the same operations on entire numbers which might contain multiple bits. So what do I mean by that? So let's say that we've got a couple numbers, and I'm going to drop down a few more lines still. And let's say that we've got a number, let's go 1, 0, 1, 1. And how about 0... Let's do 0, 1, 1, 0. I think that's 6. That's the same numbers that I was picking on earlier, wasn't I? When I added them together. Alright. Good set of numbers. I like those numbers. So, if we wanted to do, let's say, a Boolean OR, we could go down the line, and we can do the exact same logical OR here that we did with our individual true-false values. So, 1 OR 1, that is a 1. If we want to OR these numbers together, we can go down the line, bit by bit, and we can do the exact same operation on individual bits as we did with the discrete true or false values a minute ago. So if I say 1 or 0, that's going to be a 1. If I say 1 or 1, that is also going to be a 1. If I say 0 or 1, that is also going to be a 1. And if I say 1 or 0, that is also going to be a 1. I did not think ahead. I probably should have picked a set of numbers that wasn't going to just be like all ones as a result. Let's go and change this first bit over here in the first number to a 0. Then we have 0 or 0. I think that's a little more interesting. Anyway, what we have as a result of that bitwise operation, as it's known, and I guess I can label that, is we have a number which is going to contain a 1 if either of the inputs is 1, and a 0 in each place value if both of the inputs are 0. And we can, of course, do the same thing with AND, so let me go and start this over again. We can do the same thing, so 0 and 0 is 0, 1 and 1 is 1, 0 and 1 is going to be 0, and 1 and 0 is going to be 0. So now we have kind of the opposite. We have a number where for each bit, you're only going to have a 1 if both of the inputs are 1 and a 0 otherwise. So if basically the opposite of what we did the first time. So I did mention as a kind of a passing reference earlier, you also have exclusive OR, and exclusive OR, like I said, is not something you really use when it comes to general Boolean logic, because it does really boil down to just saying not equals most of the time, and saying not equals is usually easier to, like, read as a human than XOR. But XOR actually does come up in Boolean logic a little bit more often. So if I were to take my numbers that I started out with, and if I were to do an exclusive OR, which is going to result in true if exactly one but not both of the inputs are 0, and false in any other case, we can say 0 exclusive OR 0 is going to be 0, 1 exclusive OR 1, so true XOR true is going to be 0, because it will only evaluate true if one of these inputs is true but not both. 0 XOR 1 is going to be 1, and 1 XOR 0 is going to be 0. And this kind of just, like, this one turned into the truth table for, actually, now that I think about it, these all basically, like, turned into the truth tables for these operators, didn't I? I didn't really plan that one out. That's kind of cool, I guess. The last operator that I want to talk about right now is going to be bitwise negation. So bitwise negation is a unary operator. It's only going to operate on one input instead of on two inputs. It is the bitwise equivalent of saying something like not true or not false on a Boolean value. Bitwise negation is going to take, for every bit in a number like this, it is simply going to turn it to its opposite state. So if that bit is a 0, it is going to turn it into a 1. And if that bit is a 1, it is going to turn it into a 0. I don't think that one needs much further explanation. Why is like the scroll of this text editor like jittering when I get to the bottom?
Hey.
Is that another bug in GameMaker that I'm gonna have to report? That's definitely something that I don't have enough of in my life. Anyway, how does this help us? So if I scroll back up, and if I were to come back to this little player abilities thought experiment, and if I wanted to extract from this bit pattern, can the player, let's say, fly? So when I wrote out this number, the bit representing whether or not the player can fly is going to be here, the third bit from the left, or I guess you could call it the second place value. And using what we just discussed, we can do a little math operation, a little bitwise arithmetic on this number here, and we can extract the value of this bit in the second place value by creating another bit pattern which represents 0010. Basically, this is going to be the bit pattern which out of all of this represents only this value here, can fly. And I can do a little logical AND on these two numbers. And if I go down the line, so 1 and 0 is going to be 0, 0 and 0 is going to be 0, 1 and 1 is going to be 1, and 1 and 0 is going to be 0. And if I do this logical AND, and if the result is the same as the bit pattern that I want to check against, representing whether or not the player can fly, then that means that in the original number, that bit is set. And if this was some other value, let's say the player abilities value looks like this, and you do the logical AND, it's going to come out to 0. If this value is not equal to the value that we were checking against, that means that this bit is not set and the player cannot fly. By the way, there is another way that you can do this using an operator which I have not talked about yet, which you sometimes see out in the wild, but I'll get there later in the video. And we're going to look at what this actually looks like in code in a minute. But before I do that, I think it would be useful to also discuss how we can go the other way. And let's say that I have an abilities value like this, an ability flag like this. And if I want to grant the player the ability to fly, let's say they can't fly yet, but they use some item and now they have the ability to fly. What can I do if I have this number and I want to ensure that this bit is set? So I'm going to do something similar here to checking the bit. And I'm going to create a bit pattern which represents basically the true or false value for only the player can fly and nothing else. So 0010 once again. And I'm going to go and do a logical OR for each of these bits. So if I OR 1 and 0, that's 1, 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 0. I mean, I knew that I was going to say something and type another at some point in this video. Anyway, if I have this bit pattern that represents can run and can eat dairy, but not the other two, and if I OR that number with the bit pattern that represents only can fly, then what I am going to get at the other end is going to be 1011, which is going to represent, let's say, our new abilities flag. And we can say that this is like the updated abilities flag that's been modified, and now that bit has been set, and now the player can fly. By the way, and you can probably reason through this pretty easily on your own, but if you try to set a bit that has already been set, then you're just going to end up with the same bit pattern. Nothing is going to change. So if the can fly value is already true and you try to set it, then nothing changes. You just end up with the number that you started with. Anyway, so to round out this part of the video, I think there is one more operation that we might want to do, and that is going to be removing a bit. So let's say that you have this bit pattern here that represents the player's abilities, and maybe your ability to fly has worn off if that was granted by like a temporary power or something like that. And let's say that you want to remove this bit here. So this is a little bit less straightforward. If you just try to figure out how to do this on your own, it might take a little bit more effort. Feel free to pause the video here and see if you can figure it out on your own. But what we're going to do is we are going to do kind of the opposite of what we did when we set a bit. And that is going to be, instead of taking the bit pattern that represents only being able to fly and doing a logical OR and assigning that as the new value, we are going to take a bit pattern which represents everything except can fly, and we're going to set that. We're going to do a logical and we're going to take the result of that and set it as the bit pattern. So what you might want to think about it is, instead of just inventing a bit pattern that is everything except this bit, you can arrive at this number a couple of ways, but probably the easiest way to do it would be to take the bit pattern representing only can fly, and to do a... I'm going to, like, surround this in parentheses so that we remember that it's not really part of what we want to do here. We're going to do a logical, a bitwise negation, so this is going to turn from 0010 into 1101, and now we have the, like, the inverse bit pattern, as I might call it. And now that we have this, we can do a logical AND on each of the individual numbers in the abilities flag over here. And we can say 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, rather. 1 and 1 again is 1. And with this, we have successfully removed the can fly bit, and we are back with a... we can, like, reassign this like this, right? And now we have a player who can run and who can eat dairy, but who can't swim or fly. I am really curious to see if anybody has ever, like, made a game where this is, like, an accurate representation of what you're doing during regular gameplay. Like, I bet there's at least one Ludum Dare game out there or something like that that uses this as a mechanic. Anyway. This has been fun. I think it is probably time to jump back to actual code now and see some of this in action. Let's see. This... Why is the gutter so, like, wide when I have the text size set to 400%? That seems a little bit excessive. Anyway. Let me define a few numbers. So let's say var flag underscore run equals, and GameMaker, for those of you who don't know, GameMaker allows you to define binary literals in numbers by prefixing a number with 0b. And from there on out, whatever follows, it's got to be either a 1 or a 0, and it will be interpreted by the GameMaker compiler as a binary literal instead of a base 10 literal. It's sort of the same as using 0x for hexadecimal, but 0b is the binary literal in GameMaker. I can define another one, flag underscore... What was the other one? Swim equals 0b 0010. I'm going to try and space these out. Var flag fly equals 0b0100, and flag dairy equals 0b1000. So, if I wanted to have a variable which represents the player's abilities, we can initialize that to 0, for example, and then if I wanted to give the player the ability to run, I could say abilities equals abilities single pipe. So the single pipe, instead of the double pipe, is going to be the bitwise OR. I don't think I've actually mentioned the symbols that you use here in GameMaker. This is generally true across pretty much all programming languages. But you can say abilities single pipe flag run, and the player is now able to run. Abilities equals abilities single pipe flag dairy, and the player is now able to eat dairy. You can also, in the same way that you can say, instead of like n equals n plus 1, you can say n plus equals 1. You can do the same thing with the bitwise operator, so we are allowed to say abilities single pipe equals flag dairy, and this is going to accomplish the same thing. It's just going to be a little bit more concise. You might prefer writing your code like that. Now, if I want to check a bit, I can say show message player can fly, and I can use the abilities single ampersand flag underscore fly, and that is going to tell us if the player is allowed to fly or not. Again, instead of using the double ampersand, which you probably are using for logical OR, using like Boolean logic, we're just going to go with a single ampersand, and this is going to perform the operation bitwise. If I wanted to then give the player the ability to fly, I can say abilities bitwise OR equals flag underscore fly, and now I can repeat that operation, and we will be able to see if the player can fly or not. I guess I'll run the game now. Just show that the first two worked. So, when we start out, we cannot fly. You know what I should do? That showed a 4, and what I really want is, I think I said, what you really should do is check if this equals flag underscore fly. And we can do it there as well. So the logical and, when we do this, this is going to produce a number which is going to be one of these bit patterns. It's not going to necessarily be true or false. And as a general rule, the truth value rules in GameMaker will mean that like the number 4 is going to be interpreted as true because numbers greater than or equal to 0.5 in GameMaker will be interpreted as true. But for the sake of writing code that like doesn't have little bits dangling off of it, you probably are going to want to check that number is like either non-zero or equal to the original like bit pattern for the ability to fly. So we can do this again, and we now have a 0 or a 1. Anyway, if I want to take away the ability to fly, I can say abilities and equals the negation of flag fly. So like I said, when you want to remove a bit, you're going to take the bit pattern for being able to fly. You're going to do a binary negation of it so that you zero out the 1 bit and so that you set the 0 bits to 1. And then you can do a logical and that is going to remove the bit. And now when I do this, we can check if the player can fly a 3rd time, and that should successfully have erased the bit. So that's 0, 1, and then 0. All right, good stuff. So there's one last thing that I'd like to talk about when it comes to bitwise arithmetic like this. Before I get on to the conclusion of the video, which is going to be, I think, the fairly reasonable question of why you would go to all this effort when you can just use, like, a series of 4 booleans. And that is going to be bit shifting. So before I talk about the last set of bitwise operators that I'd like to discuss in this video, let's go back and do another little thought experiment where, let's say that I have a couple of, for example, player stats. Let's say player's HP equals 50 for their health. Their player's attack is going to be like, I don't know, 35, and their defense is going to be 45. And let's imagine that we have some well-defined constraints on these numbers. For example, these stats will never be, they will always be in the range of 0 to 100, or maybe 0 to 99 to make my job a little bit easier. And we know that we will never have to deal with an attack stat of like 105 or anything like that. So, and this is something that you would pretty much never do, to be clear, but I am just going to use this to create an example in base 10 that we will transfer to base 2. But let's say that we want to, instead of storing 3 different numbers for the player stats, we could just like string them together into a single number like this. And now, in the same way that we have a single like abilities flag like this and abilities mask like this for our true false values, we have a single number which has been strung together based on these base 10 numbers to represent different player stats. And I guess I should probably start with the way that you would do this is obviously going to be something like stats is going to be HP times 10,000 plus the attack times 100. That is not 10,000, that is 1,000. HP times 10,000 plus attack times 100. GameMaker plus the defense stat. And that is going to give you 50 times 10,000 plus 35 times 100 plus 45. And that's going to be this number here, right? And if you wanted to go the other way, and if you wanted to be able to derive the player's HP stat from this number, you would take this number, you would then divide it by 10,000, and you would have to either round it down with the floor function, or you would have to use integer division to so that you only keep the actual quotient and so that you discard the remainder. And this would give you the number 50. If you wanted to be able to derive the player's attack stat from this, you would have to do a little bit more work. You would have to take this number, you would have to divide it, or integer division, you would have to div it by 100, and this would give you like half of what you're looking for, but it would still have that like HP value tacked onto the end, so you would then have to use the modulo division operator, so that's going to be the percent sign or the mod keyword, and you'd have to mod that number by 100, and that would basically isolate the 35 in the middle, isolate the attack stat. So Modulo division is going to be the opposite of integer division. Instead of discarding the remainder and keeping the quotient, you're going to discard the quotient and keep the remainder. And that will give you the 35 that you want. The defense stat in this example, that's actually going to be a little bit easier because GameMaker, why are we having problems scrolling? If you took this number and if you simply did not any integer division, but if you just modded that by 100, then you would basically discard the upper 4 digits and you would just keep the 45. And this is nice and convenient, I say, as if it wouldn't just be more nice and convenient to just keep the numbers as individual variables like this. But this is nice and convenient because when you multiply by 100 or when you multiply by 10,000 or whatever, all you really do is you take the original number and you, like, slap a couple more zeros onto it. And when you then go and divide by 100, all you're really doing is taking this number and you're just chopping off digits at the end. And this is relevant because there is one more operator that I would like to discuss when it comes to bitwise arithmetic, and that is going to be the shift operators. Actually, two more operators, but like they kind of do the same things but in opposite directions. Anyway, let's say that we have like a random bit pattern, and I don't really care what the number is in this case. You could add this up and you could figure out what this represents in base 10. I don't really care. But let's say that you have a number like this, a bit pattern like this, and you want to isolate, instead of a single bit in the middle somewhere, the way that we discussed earlier, let's say you want to isolate a certain sequence of bits in the middle. So you totally could do the thing that we did in base 10 just in base 2, and if you wanted to get to these values here, you could simply do integer division and divide this number by 1000, and that would give you this value, because in the same way that when you divide a number by like 100 in base 10, you're just basically chopping off the first two place values. If you divide a number by some power of 2 in base 2, all you're doing is you're chopping off the leading place values like this. And you could, of course, take this number and you could do the same modulo division that we were doing earlier by a number that looks like 10,000 but isn't, and that would allow you to isolate this this like span of numbers in the middle. And this is totally allowed. This is totally valid arithmetic. You can do this if you'd like, but in the spirit of the exercise, there is another set of operators that you can use, which is going to be the shift operators. And the shift operators are going to, did I copy and paste this, or I just have it on my clipboard? No, I'm gonna copy that so I can not have to type it out every time. Anyway, the shift operators are going to basically allow you to add or remove leading bits to a binary number like this. It's basically going to amount to multiplying by or dividing by some power of 2 as sort of a shorthand for multiplying by like 2 or 4 or 8, or dividing by 2 or 4 or 8. And the shift operators are going to look like this. So 2 greater than signs for shift right, or 2 less than signs for shift left. If I were to take this number and shift it to the right by, let's say, 3 place values, and I'm just going to use the decimal 3 here instead of actually typing out the base 2 value. But if you were to take this number and shift it to the left, shift it to the right by 3, then we can chop off the leading 3 bits on that number. And if you want to keep it like symmetrical, you can insert some leading zeros on the other end if that makes it easier to read. And if you use the shift left operator, then it's going to go the other way. So if you wanted to take this number and if you wanted to shift it to the left by 3 places, actually, let's use a different number. Let's shift it to the left by 2 places. Then we're going to take this number and we can essentially multiply it by 4 and shift it to the left by this number of bits. So this is something that you would have seen a lot more in the old days of computers, because shifting left and right to multiply or divide by an integer power of 2 is a very easy thing for computers to do. But especially back in the day, computer chips didn't have dedicated hardware for division operators, which meant that if you wanted to divide by a number, you had to implement the algorithm in software, which was definitely not very efficient. And that's less of a concern now because pretty much every modern computer chip will have dedicated circuitry for division. It's still a little bit more expensive. I want to say it's usually like 20 to 25 individual CPU cycles to divide by a number. But that's definitely better than it was in the old days. And if you do things like low-level programming in like embedded systems, or if you're in the business of like device drivers or something, you might see stuff like this more often. If you ever look behind the curtain of what compilers do as some of their compiler optimizations, you might see something like this.
Hey.
Anyway, I don't think I ever answered the original questions in this video, which is going to be how you would isolate this series of numbers in the middle. And by this point in the video, if you've been following along, you can probably guess what bitwise operations you might want to do that. But again, if you want to pause the video and try and work it out for yourself, feel free to do that. But I'm going to start by shifting this number to the left. I can't tell my left from my rights. I'm going to start by shifting this number to the right by 3. That's going to be 1, 0, 1, 1, and then 3 zeros like this. Yes. And all I care about now are going to be this sequence of bits here. And instead of doing a modulo operation by like doing modulo division with like 16 or whatever the number would be, I am going to do a logical AND with 3 leading zeros and 4 trailing ones like this. And this is going to allow me to do when 1 and 0 is 0, 0 and 0 is 0, 1 and 0 is 0. 1 and 1 is 1, 0 and 1 is 0. Help. 0 and 1 is 0, 0 and 1 is 0. And by following this up with this logical AND, using this particular sequence of bits with this specific mask, we were now able to discard the greater bits that I don't care about. We discarded the lower bits using the shift operator, and now we are simply left with this number here, which is the number that I was interested in. Okay, so those are the shift operators. One last thing with the shift operator is that when it comes to, I'm going to backtrack a little bit to checking a bit, like I talked about earlier. And earlier in the video, I said that if you wanted to check a bit in a number, you could take the number that you want to check, and you could take the like the mask, which represents the bits that you want to check, and you could logical AND them together, and you could see if that number comes out to have any ones in it. What you could also do is you could take this number, you could shift it to the right by whatever the number of place values of the bit that you want to check is. So if I want to check the bit in the second bit from the left over here, I could shift this number to the right by 1 place value. I would get this, and now I could simply that's not what I meant to type. I could simply AND this number by 1, and I could just check if the last bit is a 1 or a 0, and if it comes out to be a 1, then that means that the bit is set. If it comes out to be a 0, that means the bit isn't set. Both of these are logically equivalent, and they both take up about the same amount of work, so really, as far as anyone's concerned, it should come out about the same. And that's true for a couple of the operations that we've done in this video. There's a couple different ways that you can arrive at various like results in what we've done here. Anyway, so I am starting to lose my voice, as you can probably hear, because I've been recording this video for like an hour 45, because I've done like 3 takes of every single one of these demonstrations and kept the version that I thought came out the best. But before I end this off, I would like to talk about actually like why can I set breakpoints in the why can you set breakpoints in notes? That doesn't make any sense. GameMaker, why are you like this? I would like to talk about why you would do any of this, because if we're being honest with ourselves, every single one of the examples that I've done in this video have been extremely, like, contrived and not something that you would actually do in an actual game. So, like this first example here, changing this set of 4 Boolean true or false values into a single like bit field, a single flag like this. This was a considerable amount of effort, and when you want to do anything with these values, when you want to check a bit, when you want to set a bit, when you want to unset a bit, You have to do significantly more work to do this than you could do if you just were using these numbers, like these values, like regular booleans, and checking like does this value equal true or not. And in the old days, this would have been done because you can't address a single bit inside computer memory, and in the days where like 64K of RAM was a lot, you actually had to be careful with stuff like this. And I'm not going to try and make it sound like you don't ever have to worry about performance, because whenever I say things like this, that's what people usually extrapolate from it. If you do the math, an individual Boolean value or any other individual value in GameMaker is going to take up 16 bytes, not 4 or 8 because it's GameMaker virtual machines reasons. But each of these values takes up 16 bytes. If you have 4 of them, that's 64 bytes just for these 4 true or false values, which is like not completely ideal, but it's also not really like world changing. For some reference, if you had like 100,000 player objects that all had these four values, then all that would add to the total amount of memory that your game uses is like 6 megabytes, which is, I mean, it's not nothing, but if you have 100,000 player objects in your game, then you probably have bigger problems to worry about. There are some cases for things like if you want to send a lot of data over a network, or if you want to write a lot of data to the disk, you might want to minimize the amount of data that you have to send over the network, or the amount of data that you have to write to a disk. And in cases like that, the argument for combining individual booleans like this does become a little bit more compelling. Now, other times where you might want to do something like this is if you have a series of properties which are all related to each other, and it actually makes sense logically to think about said properties not as individual true or false booleans, but as a group, as a collective. And this can be things like, my favorite example of this would be something like if you have an elemental type system where you have, for example, a magic spell which can have different type attributes, and if you don't want to have a whole series of booleans for like is this magical object like a fire spell versus is this magical object a water spell versus is this magical object a like earth spell. And if you want to be able to combine different properties like that in different ways, if you have a game like that with some kind of combinatorial mechanic where it makes sense to be able to just tack on one element or another, and if anytime it would make sense to be able to group a collection of properties like that together, that's when the case for creating a combined like binary value like this becomes a little bit more compelling. I would recommend against doing something like this just for the sake of showing off, which unfortunately I have to say I think a lot of people do, because it does make your code a lot harder to read, and if you come back to your code after like 2 months away, you want to be able to read your code, and you want to be able to see clearly what you were doing. Moving down a little bit, down to this, to the shift operators. So, the only place I can think of where this is regularly used in, specifically in GameMaker, but also in elsewhere, is when it comes to color values. GameMaker will store color values as a series of red, green, and blue, like, integers, but it will store them in a single value, and it will do that by taking the red color value, and it will take the green color value, and it will take the blue color value. I don't know what color this is going to turn out to be. I think it's going to be like some like light pink. And in a way that's not too dissimilar to what we were doing with this little thought experiment with the player stats, GameMaker will store your red, green, and blue color values as a single number, and it will do that by taking the binary representation of all of these, whatever that happens to be, and it will concatenate them together using the various shift operators. It will, the exact calculation is going to be something like red, logical OR, green, shifted to the left by 8, logical OR, binary OR, blue, shifted to the left by 16. And that is going to encode each of the red, green, and blue color channels just in a single number. That would be like what the make color RGB function does. And if you wanted to do the opposite, if you wanted to do something like get the red color value from a color, it would simply red equals color binary and a string of 8 ones. Green would be color shifted to the right by 8 bits, binary and that number, and blue would be color shifted to the right by 16, binary and that number. This is the only place where I can think that this sort of logic is used regularly. I am sure that there are others, but it's probably not something that you're going to encounter very often.
Hey.
If you do have a series of just red, green, and blue values between 0 and 255 and you want to convert them to a GameMaker color value, you can do this. If you want to go the opposite way, if you have a color value and you want to decompose it into its individual components, you can do this. But I would recommend, again, for the sake of readability, just using the GameMaker functions that do that for you. Now, with all that said, even if you don't use this information very often, I do think it's worth knowing this because I do think that this is one of these, like, fundamentals of computers subjects which does, in the long run, make you a better programmer if you know specific things about what the computer is doing and why. Even if you're not going to use this stuff in your day-to-day life, which I imagine most of you probably aren't, I do think that there is value in just knowing how stuff works. Now that we live in a world where any old ding-dong can go up to any old chatbot and say, hey, give me code that's going to give me, like, Grand Theft Auto 7 or whatever, and if you're lucky, the chatbot will spit out something that, like, barely compiles. Being someone who, like, cares about knowing why things work instead of just taking it for granted that these computers that we're using are magical machines that do magical things, that's going to be a skill that's going to be more important than ever, in not just in game dev, but in life in general. Anyway, so in the next video that I make, assuming that I ever get my voice back, we are going to be making some use of various bitwise operators. I'm not going to say what it is. Feel free to leave your guesses down in the comments. Until then, my name is Michael. I like wizards and dragons and making games. I like to post videos on all kinds of weird stuff you can do in GameMaker. I know that this one was more of a, like, fundamentals of computing sort of video than a GameMaker sort of video. But if you're interested in anything like this, feel free to subscribe. I have a Patreon, so if you'd like to contribute to the channel, links to that can be found in all the usual places, and if you felt like pledging, I definitely would appreciate it. You should all go check out Wizarducks and the Lost Hat, which is one of the games that I like to work on when I'm not doing YouTube stuff. Link to the Steam page can be found down below. I hope you all found this interesting, I hope you all learned something, and I will see you all later. Special thanks to Zenjamin, Zach Robinson, Squarecrow, Spy Games, Pixelated Pope, Paradox, Nykotic, Manta Ray, GameMaker, GameArt Indie, Edward Holt, DJ Gibbles, Bokeh Dev, and Argo the Knot for supporting these videos. If you want to join their ranks and contribute to the channel, head on over to the Patreon page down in the video description to join the fun.